Okay. Uh, can you all hear me and see my slide? Just write in chat box that you are hearing me and seeing my slide. Can you hear me? Just anyone confirm that I'm audible? Okay, thank you. So, okay, welcome everyone to the problem solving session for the course of analytical chemistry, which is taken by Professor Devashish Ray from IT Kharagpur. So, I am Satya Prakash Yadav, PMRF scholar from August 2020 batch. So, I am working under supervision of Professor Satish Patil at SSU, Indian Institute of Science. So, about this course, it is a 12-week course. So, in the first week, problem solving, we discussed the question related to chemical and material analysis methods.
ఏమండి
In and
ఏమండి
in week two,
ఇయర్ ఫోన్స్
uh, we have one minute, I will mute. Okay, so in the week two, we have seen the question related to role of analytical chemistry and technique. And week three, we have seen, we have discussed about chemical equilibrium, basis of the chemical analysis. And in week four and five, in the previous week, we have discussed the spectroscopic methods. And in this week also, that is the continuation of last week course. So in this week five, what are the things you have learned? So basically, in the lecture number 21, first you have been introduced to absorption spectrometry and what the instrument contained about, like light source, monochromator, sample, then transducer, and the output. And a very important law, that is Beer's law or Beer-Lambert's law. You have come across this in the lecture number one, lecture number 21. In the lecture number 22, basically you have seen the different types of transition, like sigma to sigma star, um, sorry, sigma to sigma star, pi to pi star, n to sigma star, and n to pi star. So these are the different transition and the chromophores which are having this double bond and conjugated double bond. So these kind of chromophores you have been introduced in the lecture number 22. In the lecture number 23, basically, Professor has introduced you people about the DD transition and charge transfer transition. So once the question will come, like question number 8 and 10, most probably, there I will discuss about the what are the charge transfer transition and what are the condition for that. And in lecture number 24, basically, you have come up across the FF transition. Like for the lanthanide compound, basically their EFF transition, and you have introduced to also about the shielding from the outer electron in FF transition and different types of chromophoric reagent you have been introduced in this lecture number 24. So, and in the final lecture, basically, you have been introduced to the different types of mixtures and how you are going to analyze those mixtures. So basically, if you have these two kind of compound, so how absorption came like at a particular wavelength, what is the A total is basically A1 plus A2, where is A1 is epsilon 1, B1, and C1 plus epsilon 1 basically for the particular lambda, and B2 and C2. Like that, how you have analyzed, you have come in the lecture number 25. So now I will come to the assignment problem 5. So basically, first question is, what does a spectrometer measure? So in the lecture number first, basically professor has discussed about the absorption spectrometry. So can anyone tell like what does a spectrometer measures? This is the like most basic questions for this big assignment. So anyone just write in the chat box what is the answer for this question number 1. Okay. Okay, Sweta is saying B, amount of light absorbed by a sample. Okay, yeah, thank you. So it's Nagesh and Vasantan, if I'm right, I'm saying the option. So basically, they are correct. So if I just going to discuss about the absorption spectrometry, so absorption spectrometry. So basically, where what in all we have one light source. Then basically we have a monochromator, monochromator. Then that here on one particular wavelength lambda will come. Then we have solution, basically in the cuvette. Then we have a transducer or output, basically your, or you can say that this is the detector, right? So here the intensity of light is P or AI, or whatever you are saying, P0, I0, and once we pass through the sample, the right. So the fraction of light will be absorbed by sample and in intensity after the passing through the solution is. So basically, what we measure, basically the absorbance, which is the negative logarithmic of I0 by I, right? Or you can write log I by I0, whatever it is. So here basically, first lies that Lambert-Bourguier law. Lambert-Bourguier law. So what they found that the absorbance is proportional to the length of the cuvette. So basically your cuvette will be like this. So what is this length? That the absorbance is proportional to the length of the cuvette. And the second one is the Beer's law. So Beer's law said that the absorbance, which is the log of the I by I0, is nothing but proportional to the your concentration. So if we combine, then we have absorbance is proportional to B and C. Once we remove the proportional, then we will get a proportionality constant, which is epsilon BC. So this is called molar absorptivity or molar Exactly. Right. So why this lies only card likes people say that beer Lambert's law or only they say Beer's law because length we can fix it like we can fix a cubit basically standard cubit coming 10 mm or sometime we have 1 mm and 2 mm, right? So this length has not as important in the analysis of a mixture, but concentration is a very important parameter. That's why we basically instead of saying Beer-Lambert's law we just say that Beer's law. So that is the main part. So here we basically measure in the spectrophotometer the amount of light absorbed by the cell. Is it correct? So I think this will give a brief idea about the what spectrophotometer and why this called Beer's law and this Lambert-Bourguier law also introduced and Beer's law. Okay. So now question two is the which light source can be used in the absorption spectroscopy. So anyone if they have seen the I think lecture one in the lecture one only professor has introduced about the different types of light source. Okay, Sweta yes is saying okay, anyone else? Okay, so actually Sweta yes is right. The answer is A. Which light source can be used in the absorption spectroscopy? So the thing is that why we have to choose the light source first. Like why the choosing the light source is very important. So this is the first compartment, like first unit of the absorption spectrometry. So light source. So basically, selection of light source is very important because of their wavelength range. In what range they give the in what range of wavelength they give the photon. So that is very important in the UV visual absorption. So if I see the so in UV visual absorption spectrometry, basically people use different type of the lamp. So yeah, so people use xenon arc lamp, and people also use hydrogen and deuterium lamp, and third is tungsten or halogen lamp, and people use this numbed glower, nichroma wire also used, nichrome wire, and one more is global, right? So first is that what wavelength range, like what wavelength range light these sources give. So xenon lamp basically you will give 250 to 600 nanometer, right? And hydrogen and deuterium you will give you 160 to 380, and this tungsten give 240. Sorry, tungsten or halogen basically you will give to 240 to 2500. Next, glower you will give 400 to 20,000 nanometer, and nichrome wire they give 750 to 20,000 nanometer, and your global give 1200 to 40K. nanometer. Right? There are things like what are the why which lamp is suitable. So the thing is that that is decided by lifetime, cost, and this wavelength range. Three factor basically people choose to. So suppose I have a spectrometer in my lab, which can go from 160 to 2500. So can anyone guess? So here people can use one lamp or people can use the combination of the lamp. Can anyone tell which two lamp I can use and get this entire wavelength region? So, and the question is why these wavelength range are important. So, suppose if you will go and see the different type of electronic transition, there you will see that if your absorption maxima is close to 200, right? 200 nanometers. Suppose you have this your A max and this is your lambda. So we can't use this tungsten lamp and xenon lamp or Nostra Glover lamp or something, right? So for that you need the combination of the two lamp like that. So the question is here. So if I want suppose a wavelength range of 160 to 2500. So we have like one ocean optics uh, this lamp. So basically that combine two types of lamp. One is the deuterium lamp, other is the halogen lamp. So so for the visible region, basically we have 160 to 380, like nice wavelength range from deuterium, and after that like, 250 to uh, 2500 we have this halogen. So this way like you can combine what are the different wavelength range you want. So here the very simple question, which light source can be used in the absorption spectroscopy. So as you can see that 400 to 800 that is your visible region, and like to 160 to 400 basically your uh, UV region. So we can see that like some part of the UV region is falling under the tungsten line, which is 2400 to 500. So tungsten line can be used in the UV region, visible region, and near IR region. So your near IR region is basically 800 to some 2500. So what is spectrometer we have, which can go from UV to visual to near IR. So there are compound like very less number of compound is available which give the absorption in the near IR region. Means the electronic transition is very small. So basically those are found in the this polaron. Once we find the polaron, then like we will see the absorption in the near IR region. So basically you have to solve this question, you have to see that what are the sources available and which source give the exact wavelength range which you want. So basically for UV visible, this tungsten lamp is the right choice for this. Okay. So let me go to the question number 3. So which ion among the following if present in the color complex of the metal ion decreases the absorption? So any guesses for this? So I think if I am right, if you have seen the lecture number 22, then definitely you can answer. Okay, so maybe where I say B. Great. Yeah. Okay. All right. So Soumyadeep Ore is absolutely right. So basically that phosphate and sulfate. These are the interfering anion, right? So suppose This first of thing, then the what does mean the colored if you have a colored complex, so what will happen? Basically you have this absorption, sorry, this absorption maxima, you have something like, so okay, fine. So this you have some absorption A1. This is the colored complex, right? So color, the like color complex, basically your absorption. If you have this color complex, so basically your epsilon is C, right? So this epsilon will be very high for this one. So what is happening, if you're interfering in ambient region, that will form some colorless colorless compound, right? So suppose you have this colored compound, the absorption uh, correspond to the colored compound is A1, so which C concentration is C. Once the interfering anion is present, they will form a colorless complex. Then what will happen? Your C will decrease, right? C will go to the C1. Okay, so your A1, so A2, so this is C1, A2 will be C2. So your C2 will C2 is less than C1, so your absorption will also will be less than. So what will happen? This time it will go and come like this. So this is your it. So make sure that this is the interfering anion. So what interfering anion basically do? They do the, like, they decrease the absorption because they form a colorless complex and decrease the concentration of the colored complex. So this is the reason why the uh, like absorption decreases. So what is the characteristics wavelength of the acetyl salicylic acid in the UV visible spectroscopy? Anyone? I think Professor had discussed in the lecture number 22 or 23 where he discussed about the chromophores. So I know this is like this is not a conceptual question, but you have to like regard the UV visual spectra of acetyl salicylic acid. And then anyone can write in the chat box. I will write the structure of this acetyl salicylic acid. So Neil Pawar is saying 285. This is salicylaldehyde. So basically your sorry, salicylic acid. And if here have this H, so this is salicylaldehyde, and this is acetyl salicylic acid. So yeah, Sunil is right. The like salicylic uh, salicylic have the, sorry, okay, how to delete it? Okay, so basically if you can see that this aspirin, which is a like a drug people used to take during like headache, something like that, that is painkiller. uh, and so if you see, I have written, I will just remove that. Okay, if you can see that UV visible spectra of this acetyl salicylic acid. So it has this absorption maxima. Basically, your this is the epsilon molar absorption. So this is close to 285 nanometer. So the answer is N, and this epsilon, which is your molar absorption, is around 400. Right. So that is the answer for the characteristic wavelength of acetyl salicylic acid. So this is just we have to memorize, but we can remember the range where it will come close to 300. So in unconjugated alkene, pi to pi star transition takes place around. Can anyone tell like, where it will come? Pi to pi star transition? Oh, Sweta yes is saying D. Okay. Anyone else? Anyone else who has different answer than Sweta? Oh, Sunil is also saying D. Okay, so the answer is different. What Sunil and Sweta is saying. So unconjugated pi to pi star transition takes place around. So I will go through little bit in detail. So first, what is the ligand transition? So basically, ligand have this kind of period. We have energy level like this. Okay, so this is your sigma. This is pi. Then we have non-bonded, basically called n, and then pi star. Then we have sigma star. So once we have this like molecular orbital, two molecular orbital, so basically they will overlap and form one bonding, and other one will form the antibody. So the more stabilization happen in the down, the other one will go more up. So basically your sigma will be lowest, then sigma star will be top, then pi star, and the non-bonded one will be the same level what the like molecule energy is there. So this is the energy level. Now, what are the favorable transition we have? So basically, we have one is the sigma to sigma star, and other we have the pi to pi star. Then we have n to sigma star, and we have n to pi star. Now we have to see like which one will be the highest energy. So your sigma to sigma star will be the highest energy, as you can see the gap. Then next one will be what? Next one will be n to sigma star. Then we have, then what we have, I think most probably we have n to, sorry, pi to pi star, and then we have n to pi star. So these are the four transition which is there. So sigma to sigma star, you can see that it is the highest. Then other is n to sigma star, and then pi to pi star. Then the lowest one will be the your n to pi star. So other transition are forbidden, because then you have to go to the concept of this zeroed and non-zeroed. So basically G to U are allowed, because here your transition moment is not zero, but G to G and U to U is forbidden transition because transition dipole moment will be the zero. So these are the concept. So first thing is that if I take this suppose I will take for example of sigma to sigma star, which is your CH4. So what it has? It has absorption is close to 122 nanometer, right? As you can see that because the energy gap are the very high. Then if we come to the N2 sigma star, they have like they will go little bit more. But suppose if I come, so this is one term is there called unconjugated alkene. Unconjugated alkene means it has only one CC bond like this. Okay, so these have the like absorption close to 170 nanometer. So if you have like carbonyl, it will be 190 nanometer. Right? So N2 pi star basically will come in the range of this 250 to 270 nanometer because as the orbital will be close, energy will be less, wavelength will be more. Right? So this is the basic. So your pi to pi star transition for unconjugated alkene will fall in the region of 170 to 1. But if it is conjugated, then there are a rule called Woodward-Hoffmann rule. Basically, there we have these rules for if we have two conjugated like alkene, or once we increase the like conjugation, how the this wavelength will increase. For the example, this professor has discussed about the carotene. It has close to I think 11 conjugation. So that will increase to 400. This 170 will go to close to 400, right? But here it has asked about the unconjugated alkene pi to pi transition, which will fall in the range 170 to 199. So I think now is it clear that question number 5, the answer is B? Yeah, great. Thank you. So this is the way like you have to know the range for sigma to sigma star, sigma n to sigma star, and pi to pi star, n to pi star. But the thing is that these are the only for the unconjugated. But once we increase the conjugation, basically homolyl LUMO will come closer, and that's lead to a less like energy transition, and will increase the larger wavelength electron. So the next question is what is the maximum absorption of caffeine in the UV visible spectroscope? So any guesses for this caffeine? Okay, saying A. Okay, anyone else? Yeah. So you both were right. I will write just caffeine structure. Okay. So this is basically your caffeine. Caffeine. Okay, and its UV visible spectra has shown by professor already. So if you have watched the lecture number, I think most probably 22 or 23. I don't know. Yeah, it will be in this lecture only. Yeah, 22 only. So this is the UV visible absorption spectroscopy for caffeine. So we can see that range. This will come close to 270. And the important thing is that this molar absorptivity is very high, close to 1000 for this caffeine. So this like you have to either you are working in this area, then basically you will remember what is the absorption. But you can guess how it will be close to 270 or 280. So again, this is the same related question from the previous question, but here it is saying that what is the maximum absorption wavelength for caffeine in the water? Can anyone guess like what should be the answer? Because you have already seen the uh, 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 like caffeine UV visuals. What is the maximum absorption wavelength for caffeine in the water? Basically in the aqueous solution. Can anyone write in the chat box? Yeah. So the answer is right. Like, but the thing is that what here you have to write, what you here you have to note is that one thing. Basically, this is the solid state. So once we put in the solution, so what will happen? So basically, your wavelength, maximum absorption wavelength, will shift according to the solute solvent interaction. So, so if anyone is more interested, like how, like what is the effect of solvent on the absorption of, so they can go through the this iodine, like uh, basically UV visual absorption spectra of iodine in different solvent. Suppose you take the like methylamine, water, iridine, so many other solvent. See, so if you go through this UV visual absorption spectra of iodine in different solvent, then you will see that what is the effect of solvent in the UV visual absorption spectra. So this is, I think, one experiment in the master's courses. So you people can go, because for that I have to show the spectra and all. So this is the this, because here the absorption wavelength for caffeine in what aqueous solution is not changing much from their or like solid state absorption, which is two like 272 nanometer. But if you want to see how this affect, then you have to go through this experiment, UV visual absorption spectra of I2, see like different solvent like water, ammonia, pyridine, methanol, ethanol. So you will see that how what is the solute in a solute which is I2 and solvent interaction. This side. So, what types of charge transfer occur if a complex have ligand with relatively high energy lone pair, which is, for example, this sulfur or selenium, or if a metal having low lying empty orbital? Can anyone guess what is the answer for this question? What types of charge transfer occur if complex have ligand with relatively high energy lone pair, or if metal have low lying empty orbital? Okay, silicon to metal charge transfer, Sweta and Samiti Parasing. Yeah. Okay, so that's great. So basically, if you want to understand what is ligand to metal charge transfer, right? Then you have to see that from where the charge transfer happen. So basically, here it is happening from ligand to metal, right? So basically this has to be electron density rich, okay, and this has to be electron deficient. then only your like charge transfer will happen from ligand to metal. And other thing is that they should have the comparable energy. So if we consider about the like molecular orbital, so whatever their this lone pair electron energy level and this low line this empty orbital, they should have the comparable comparable energy, then only this metal to charge transfer happen. Suppose we have this, here we have ligand lone pair and the other one is with slightly lower or higher. This is your low empty metal pair. So what will happen? Basically, your overlapping of orbital will happen, and it will form one bonding orbital, another will be the anti-bonding orbital. Right? And the transition, whatever is happening from bonding to anti-bonding orbital, which is called the ligand to metal charge transfer. So, what are the criteria for the ligand? So, for ligand, if we are discussing about the what are the criteria for ligand in the ligand to metal charge transfer. So first thing is that it has to be a low electron affinity. Low electron affinity means it should have the field orbital of fairly high energy, and it should be readily oxidizable, right? So readily oxidizable means it should immediately give the electron to the metal center. So that is the ligand criteria. So low electron affinity and nearly readily oxidizable. So you can see that like different types of ligand and their ligand to metal charge transfer absorption spectra. Other one is for the metal. For the metal, they should have the electron deficient. So for electron deficient, they should have the they should be in the high oxidation state. High oxidation state. So you have to see that where the metal will be the in the high oxidation state. If it will be the high oxidation state, means their orbital will be the empty. That like LUMO like highest like LUMO will be like lower in the energy if it will be the if it will be in the higher oxidation state. Right. So this is the condition for the metal, whether it is electron deficient and it should be the high oxidation state. So once you see that metal, so suppose if I ask MnO4 minus, what will be the charge transfer? It is metal to ligand transfer and ligand to metal charge transfer. So you know that here Mn is in plus what is plus 7, right? Plus 7 oxidation state. So it is in high oxidation state. So definitely your ligand to metal charge transfer will happen. So it's like that. Suppose this, if I ask you the one about a ligand, so you choose the cadmium sulfide. So here sulfur is like electron rich. It has high energy lone pair, and it is readily oxidizable in low electron affinity. So here is also ligand to metal charge transfer. So you have to see the condition. If you are in competitive exam, you are asked like try to find out what are the what types of transition is. So you have to see the like condition. Okay. So the question is which among the okay. And now I'm going to question 9. So which among the following reagent can be used as a reagent for simultaneous spectroscopic determination of palladium 2 and gold 3? So any guesses for this question number 9? Can anyone just write in chat box what should be the answer for this uh, question? So I will just try this. Okay, Sweta, yes, is saying A. Anyone else? Anyone else? Anyone else has different answer than Sweta? Okay. Sunil Pawar is saying C. That's great. Anyone else? Okay. Can anyone tell me like what is the concept behind this? Like if you want to simultaneously spectroscopic, if you want to determine simultaneously this any two compound, what you see first? Anyone like suppose if I give two mixtures, you want to spectrophotometry metrically you want to determine what you see that whether it can be determined or not. Anything, any curve which you have come across during the lectures. Okay, so I will write some spectra. Okay, so this is your A, this is your B, this is your A, this is your B, this is your suppose A, somewhere your this is B. So can anyone guess in which case like we can determine that A in B? If I say this is 1, this is 2, this is 3. Okay. Sunil Pawar is saying 3, Sweta is saying A. Okay. So basically in A and B, both the cases we can determine the A and B. The main idea behind this, so we knew that epsilon will be epsilon lambda. For a particular lambda, there is a molar absorptivity. So the idea is if we want to determine A, so here what will happen? Your spectra will come like look like this. Okay, this if we change, basically your A is equal to A1 plus A2. That is the concept. Now, what is the idea here? So the idea is that you form such a complex where once we are going closer to a compound like this molar absorption like absorption wavelength maximum, there the absorption from compound B should be close to zero or minimal. Then only what we can say that, so for lambda 1 we have this A is equal to this whatever absorption will come will close to will nearly A1. So we can take the assumption and determine that. For A2, this will A total at wavelength this lambda 2 will be close to it. So that is the concept. like you have to separate out. So we have to find out that which is the complex that led to and goal 3 will form a complex such that it has, this one has some particular lambda max and epsilon. This also has some different lambda max and epsilon. And other thing is that they are more or less separated. So the compound which is called this methionine paragene hydrogen chloride. So I will write just a structure for this. So we have this benzene N S, okay, O. So the structure is like something like this. So it form a 1:1 complex with lead and lead oxide. Sorry, palladium and gold. So this your palladium, it has maximum absorption around 480 nanometer and molar absorption is 3.6 into 10 to the power 3. You write liter per mole per centimeter, right? Gold has absorption maxima around 630 nanometer, and your this epsilon is also 1.3 into 10 to the power 4. So the first thing is that see the molar absorption, which is very high, like 10 to the power 4 order is a very good molar absorption. So for DD transition, you see it will be on the order of 5 to 100, close to 5 to 100, which is very less. But here, first thing is that it's a mostly charge transfer complex. That's why we have this your epsilon max is very high. And second thing is they are separated by their absorption maxima is separated. So that's where we can find out the methio me paragene hydrogen chloride, which is also called MMH, right? So other option you have to find out those complexes like lead, palladium EDT and gold EDTA, and you see how absorption spectra came, whether they are separable or not. So the idea behind this is that if near to the A absorption maxima, the absorption from B should be minimum or close to zero. Absorption at the this like maxima, the absorption from A should be minimum or zero. So now, is it clear why the option B? It is forming two different complexes. It is forming complexes with palladium and gold, and giving the different absorption wavelength maximum. Okay, thank you. So now, question number 10. Which is the example of the MLCT among the following? So first is uh, this is PB3O4 cadmium sulfide K2MnO4 N iron OF Fen3 2 plus. So okay, Sweta yes is saying D. Great. Anyone else? Anyone else? Okay, Sunil is also saying D. Okay. So why not B or A or C? There, what kind of okay, okay. Why not ABC? What kind of charge transfer you people are see? Sikha Saxena ma'am is also saying D. Okay, it's great. So A and B, on what basis you have removed like ABC? Okay, I think everyone is right. I will just go through it here. So your ligand should have low lying pi star orbital. That is the first criteria, and your metal should be in the low oxidation state. Then only it can give the electron from the metal to ligand. And second thing, the most important thing, that their energy should be comparable. Now coming to the this Pb3O4. So it is in the oxidation state of what? So if I write 3x plus 8. Okay, basically it has 2 PbO plus PbO2, right? So it's okay. So basically here you're lead in the higher oxidation state. So basically it will form the other way. Your CATS sulfide, I already told here, like where is that? Here, cadmium sulfide I has given option in the ligand to uh, metal charge transfer, because here we have the sulfur and selenium. They are having high energy lone pair, or you can say another low electron affinity and readily oxidizable. Your K2MnO4, here also this manganese you're in 6 oxidation state, which is very high. So it is already electron deficient, how it will go. But here your iron in the iron 2 plus. Iron 2 plus means it should be in D6, right? Okay, iron where it from? Yeah, it will be D5 D6S2, then 2 plus oxygen, this will be D6. Now if we go in the octahedral environment 5, it will go into the T2G, and here we have EG, right? So I can just that's okay. So here 110 ferranthalene, this is, I can just write the structure last in the last lecture I have written this already, so I will just write once again. We have 3 engine, just we have this. So here we have two ends. So this is the coordinating site. So and it will form this octahedral complex. I already told. This is the bidentate ligand. So it should be like this or other way. So this you have 6 electron, and it is a strong field ligand. So it will form a low spin. So it has 6 electron, right? So T2G, and this 110 ferranthalene has your other things, low lying pi star orbital, right? So the transition between T2G and pi star orbital of 110 ferranthalene phenanthrolene, or fen basically we say, that will give your metal to ligand charge transfer. So basically you have to know what are the ligand which can form this metal to ligand charge transfer. They should have this low lying pi star orbital. So basically your cyanide, thiocyanide, CO, pyridine, like bipyridine, this O on orthophen, and this dithiolene. Okay, so these are the ligand which are having the low lying pi star orbital. So you have to see that where these ligands are, and and other thing you have to see that the metal should be in low oxidation state. So that two thing if it match, you can easily uh, like uh, 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 guess the answer. What is the answer? Okay, so thank you for your patience and involvement. So these are the things which I will upload anyway, that spectra I have given. Okay. Okay. Thank you all for joining.